I'm going to discuss how we go from Maxwell's equations to finding equations for E on its own and H on its own. We're going to assume that we're working in the standard linear isotropic homogeneous materials, which we often abbreviate to LIH. And what this means is that we can write D is equal to epsilon naught, epsilon R, E, which you can also write just as epsilon E, where epsilon stands for epsilon naught, epsilon R. And similarly, B is equal to mu naught, mu R, H, which can also be written as mu H, where again mu is mu naught, mu R. You'll notice that we have D and B together on the left-hand side of those equations without any of the multiplying constants, and you have E and H on the right. D and B, of course, also share boundary conditions, as do E and H. So that's why we tend to group them together, and we're going to think about E and H today. Our starting point is going to be the Ampere-Maxwell equation, which we'll write as the curl of H is equal to J, remembering those are free currents, plus dd by dt. And what we want to do is we want to turn this equation into an equation involving just H itself. We just want to do that. There's going to be a number of steps along the way. So the first thing we're going to do is we're going to assert that in a conducting material, the current density is equal to sigma times the electric field. This is actually another form of Ohm's law, which we normally write as V is equal to IR. You can construct a justification for why this might be true using the Drude model of metals, conduction in metals, and I will put together a video to cover that just to indicate. Of course, the true quantum mechanical many-body problem is significantly more complex, but this is a useful approximation for now. So we can write the curl of H is equal to sigma E, and we're going to convert the D on the right hand side into an E, so we'll just put that as plus epsilon dE by dt. We are, of course, here assuming that epsilon itself is time independent. Epsilon naught is always time independent because it's a constant. Epsilon R is a material dependent constant, well, a material dependent property, which could be time dependent, but in general we assume that it's not. Now, how are we going to eliminate E? We're going to eliminate E using Faraday's law. So Faraday's law, you will of course remember, is that the curl of E is equal to minus dB by dt, which of course is just minus mu dH by dt, again assuming, let's just change that T to look a little bit more like a T rather than an epsilon. Again, we're assuming that mu does not depend on time. So we know how to replace curl of E with an H, so what we need to do is come back to the Ampere-Maxwell equation and take the curl of the whole thing, so that the terms in E on the right hand side are all written in terms of a curl. When we do that, we find the following. We have the curl of H, and notice that the order of brackets here is important. I've kept the brackets around curl H because that's a vector. You cannot just change those around. And that's equal to sigma times the curl of E plus epsilon d by dt curl E. We've changed the order of differentiation on E, and unless we're in a very, very unusual situation, that is perfectly acceptable. We'll now expand out the left-hand side, so we'll recall that curl of curl can be written as simply the gradient of the divergence minus del squared. And the gradient of a divergence is not the same as del squared. If you write out the Cartesian coordinates, you can see that. And on the right-hand side, we will just simply substitute for curl of E as we've written already. So we have that the gradient of the divergence of the h field minus nabla squared, del squared, however you want to refer to that second derivative of h is equal to sigma, sorry, let's put the minus signs outside, is equal to minus sigma mu dh by dt, and that's just substituting of curl E, minus epsilon mu d2h by dt squared, and that's doing the second differentiation there. We know already, because we have asserted this on multiple occasions, that the div of h is axiomatically equal to 0. People have actually managed to construct something that looks very much like and behaves like a magnetic monopole in a material, though it is not a magnetic monopole. If we have time later in the course, we will talk about how we've done that. So for now, we are continuing to assert that div of h is equal to 0, which leaves us with just the del squared on the left. We are going to assume for now that we're actually dealing with a situation where sigma, the conductivity, is equal to 0. That doesn't really change anything. If we were to leave sigma non-zero, then that term in dh by dt would just be a damping term. So we're not actually removing anything. And so we find that we have del squared h is equal to epsilon mu d2h by dt squared. And this is simply a wave equation, and we have a wave speed which is given by 1 over the square root of epsilon mu. If we're in a situation where epsilon is equal to epsilon naught and mu is equal to mu naught, i.e. we're in a vacuum, you'll find that that number is exactly equal to the speed of light. And this in fact was what gave Maxwell the clue to think that light might well be some kind of wave involving electromagnetism. In a paper in about 1865, he in fact notes this. He says that the similarity is so close that we should perhaps draw this inference. We can do the same for E, so let's just turn to that now. For E, we're going to start with Faraday's law, so we're going to start with the curl of E is equal to minus dB by dt, and we want to substitute for B using, so we will use the Ampere-Maxwell equation, but written in terms of B. So we're going to have curl B is equal to mu J plus epsilon mu dE by dt. That's how we're going to do that. So how we need to go back to Faraday's law and work out a way to have curl B on the right hand side, and of course we do exactly what we did just now for H. We take the curl of, again keeping the brackets, the curl of E, and that's equal to minus d by dt of curl B. Expanding out as we did before, we find that we have the gradient of the divergence of E minus del squared E is equal to minus d by dt of mu. Now J, of course, let me just note this up here, J can be written as sigma E, we've already noted. So when I come down here, I'm going to say minus d by dt of mu sigma E, just to save a bit of time, plus epsilon mu dE by dt, and we're nearly there. So first of all, we note that div E is equal to 0 if rho is equal to 0. We're going to assume for now that there is no free charge, and so rho is equal to 0, so we can discard that term. And so we get the following. We find that del squared E, and I'm eliminating the minus sign on the left and the right, is equal to, again, setting sigma equal to 0, so dropping the first term on the right-hand side, we get epsilon mu d2e by dt squared. And again, I said sigma is equal to 0. And this, again, is a wave equation with speed. over the square root of epsilon mu. So this is just a simple rearrangement of the Maxwell equations. So we started with single derivatives in terms of time and space. In both cases, for both E and H, we're working with the curl equation, so curl of E or curl of H. By taking the curl of that again, we end up with the second derivative in space, d2 by dx squared plus d2 by dy squared plus d2 by dz squared. That's the del squared term. And on the right-hand side, we end up with a d by dt of the other Maxwell equation involving a curl, which introduces the second derivative in terms of time. That's about as much as I want to say on this topic. Do make sure that you understand how these manipulations work and where all these different terms come from, because it's important in understanding the whole of electromagnetism.